Anything before we get going?
How would you say you calibrate the calorimeter?
I'm good.
Would you just say you
I'm going to record today's lecture and put it on my YouTube channel. If you want to watch that, I do have a YouTube channel. It's all just presentations for classes.
What's your YouTube name?
What's that?
What's your YouTube name?
So if we need to see this lesson again.
I was gonna
Probably on my
say.
Google, I know it's 00 Stickles. But I know that I have at least one person that is out of town, so and asked me to record the lecture, so that's what I'm doing.
Where's your record?
What's that?
Where's your record?
Sarah Bailey.
So like, if we're gonna be gone and be like, hey, can you record the lecture? And you would?
Yeah.
Amazing.
All I have to do is ask.
We'll just use that.
You just have to, all I have to do is ask. I'm more than happy to. I might record more of them now anyway, just if I can use the laptop. The 19th? It even says that on the screen. It does say that. So, anyway. Last time we talked about extrapolation techniques to do derivatives. But we can do extrapolation techniques in general. So let's do that and see if we can apply it to a specific scenario and then do a little bit of stuff in Excel to be able to talk about how we can use these extrapolation techniques to approximate derivatives. And then on Thursday, we'll probably talk a little bit about how we can do it with integrals as well. Right? So let's look at, let me shut that line back there.
This Thursday is the homework day.
Homework is due this Thursday.
We didn't have a quiz this Thursday?
Tuesday. Next Tuesday.
Whoa, when was that now?
Huh?
When we announced that?
Last
When we
time.
talked about
Because I asked when if you wanted it this Thursday or next Tuesday. And everybody goes, next Tuesday!
Yep.
Kind of like at that volume.
My mind is very weak right now.
that makes it so much better.
Oh, I didn't even write it down. That means it's not real.
It's not real?
If it's not in my planner, it doesn't exist.
And we'll talk more about the quiz next time as well.
It's a quiz?
They're all called
I
quizzes.
lied. I did put it in my planner.
Yep.
I was in the wrong page. It doesn't
It does exist. All right, so to that end, so remember last time, the whole idea behind the Richardson extrapolation is to use a formula that you know with a certain error bound to try to get another formula, might be slightly more complicated, but with a better error bound. So that'll get you the approximation that you want more quickly. So let's say we did that in general. Say we had some function q of h that was approximating some quantity f, and the error depended on some h to the n plus some other terms that were higher powers of h. Yes?
What is this called?
Richardson extrapolation?
Oh, okay.
Yeah, it's
We're
just,
still on that?
we're still on that.
Okay.
Yeah. I mean, I can give it a different name if you'd like.
No, that's okay.
You know, Kroll is a very famous name in math. In algebra. Yeah, it is. Kroll? Yeah, absolutely.
I don't believe that.
You don't believe that? There's no such thing. Go look at it. You can do a Google search for Kroll monoid if you like.
For what?
Kroll monoid. M-O-N-O-I-D.
Even coding language named after people, yeah.
It's a big time algebra race, right?
Yeah, Kroll, yeah. Kroll's a big time algebra. It's
Well,
pretty
it's
good.
not related to anyone in my.
Anyway, so the whole idea here is that we're using this function q to approximate this quantity f, and then we've got error on the end that depends on h. So this part right here would actually be O of h to the n. The whole idea, though, is to try to use the previous known formula to get us f, to get rid of the h to the n and make it O of h to the n plus 1 at least. Okay. We did this last time specifically for the derivative, right? This is what we did at the end of class last time. So we're just doing this in general and seeing what the formula will come up with, and then applying it specifically to the derivative, and get some approximations that way on Excel. So again, just to reiterate, this function q is being used to approximate f. Right now, the function q has error term that's bounded by essentially a constant times h to the n. Okay, that's the idea. So what we want to do is try to kill off this kh to the n term and make it something that's in terms of h to the n plus 1 instead. And again, if h is small, h to the n plus 1 is smaller than h to the n, so we get faster convergence by taking smaller values of h. That's the whole idea of doing this. Okay? All right, so we're going to do the same trick that we did last time. We're going to put in h over 2 for h. So this is the same thing that we did last time. Still have f, because again, we're using this to approximate the f. We get plus k times h over 2 to the n. And then putting h over 2 in here, well, if I put 2 in here, I'm going to get an over 2 to the n plus 1. Probably makes that smaller, but at worst, it's O of h to the n plus 1. It doesn't really change this other piece here. Basically, all we're saying is that I'm putting this in here. I'm still going to have terms that involve h to the n plus 1, h to the n plus 2, and so on down the line. Okay, so I still would have O of h to the n plus 1. That's an n.
The key would change or would it be the same still?
It's a constant, so it stayed the same. I wanted to stay the same because I wanted to kill that term off.
But if you're keeping the f constant as, would we have to do something about the k? Because you could change the variable.
All we're doing is just replace. That's a true statement. So whatever I plug in for h. So if I replace h with h over 2, it's still a true statement. That's all we're doing. We're just reevaluating the function in h over 2. So instead of saying evaluating at 1, we're evaluating at 1/2.
All right.
Yeah.
Oh, yeah, no. Yes.
The last h.
So if I put h over 2 in front of each h's over here, I'm dividing by a 2 to the n plus 1 essentially, which all that's going to do is make it, since n is a positive integer, it's just going to make this smaller. So this O of h to whatever is just an upper bound. If I'm making it smaller, it's still an upper bound, not those terms. If this were 5, if I divide it by 2, it's still bounded above by 5. So all I'm saying is it can't get any bigger than this. It's probably smaller, but it can't get any bigger. In fact, it should be significantly smaller, but I'm not worried about that smallness part right now. Basically, all I really am caring about is trying to get rid of this term and leave it in terms of these higher power terms. That's all we're trying to do. All right. So if I want to kill off these two terms, what's the denominator going to be in front of this k if I simplify this term? 1 over 2 to the n, right? So I need to multiply this by 2 to the n and subtract, right? So if we do 2 to the n times the q of h over 2, and then subtract off q of h, again, the f is some constant quantity that we're trying to approximate. So we'll have an f that we can factor off. We'll get 2 to the n minus 1. Why do I keep my n's keep looking like h's? 2 to the n minus 1 times f, right? Because we took 2 to the n times this and subtracted up and factored off the f. These cancel. And over here again, these two terms are something times h to the n plus 1. I didn't add any more h's, right? Right? Didn't add any more h's. In fact, I just multiplied this by 2 to the n. There's going to be at least one copy of a 2 in all the denominators. So again, at worst, it's going to be on the order of h to the n plus 1. I didn't multiply by any h's, I didn't divide by any h's, I multiplied by a 2 to the n. In all of the denominators in that h to the n plus 1, there's going to be a 2 to the n plus 1 at least, right? So if I multiply by 2 to the n, there's going to be at least a copy of 2 in the denominator. It didn't make it any worse.
So if it was something a constant times s n plus 1, would it still be? Would we still write OH n plus 1?
No, because in that case, if it were, well, multiplying by that 2 to the n, that n matters in that case. So it would be 2 to the n h n plus 1.
Oh,
And then, because then the 2 to the n would grow as the n grows.
but in this,
Yeah.
what we're saying is since the denominator, there was still 2 divided by 2n.
Right.
Which is multiplying smaller than 2n.
Right, because if I had that h to the n plus 1 originally, we replaced it with h over 2. Right? And then if I multiply by 2 to the n, there's still at least a 2 in there. So I didn't change the order of the h's at all. That's what I mean. And that's actually important because I don't want the error to get worse. So I don't want the error to depend on the n, except for in the h. Okay, that's important. Okay, we okay with that? Yeah, Grace.
Why is it 2n minus 1? What is that?
Okay, so I multiplied this one by 2 to the n, so there'd be a factor of 2 to the n out in front of this f, and then I subtracted. Yeah, Morgan.
So how come when you subtracted your second from your first equation for the third term, like why would those cancel out for the on the order?
These two,
Yeah.
because this one really has a bunch of 2 to the n's plus constants in them. This basically just means you've got some polynomial in h to the n plus 1, right? So when I divided all of them by 2 to the n plus 1, oh, this would be 2 to the n plus 1, this would be 2 to the n plus 2, and so on down the line. The constants won't match the other ones, so they won't cancel out exactly. Because when I multiply this by 2 to the n, this one still has a 2, this has a 2 to the n, all right. This one has a 2, this one has a 4, and so on down the line. It's a good thing I'm recording what's on the chalkboard for Sarah. Susan, that's right, Susan.
Is it recording your voice?
Yeah. It does, it's recording my voice on it. So, anyway. So if you're gone and you ask me to record, I'll probably say something about you on there just because.
You're gonna post a link to your YouTube channel on Google.
I
Found
can.
it.
What's that?
I'll send you one.
Okay, cool.
Did you already find it? Okay, there you go. There's how many more subscribers I can get after today.
I'll subscribe to them.
Yep, sure. There's lots of cool things like all sorts of math lectures on there. It's just me talking, so it's not very interesting. All right. Anyway, remember again that we're trying to approximate the f, right? Okay. So if I divide through by the 2 to the n minus 1, I get this expression that looks like our f is approximately, again, it's approximately because we're thinking of this as being the error term. The h is small, so this should be small, right? So we're approximating the f with 2 to the n q of h over 2 minus q of h all over 2 to the n minus 1. Now, what's the order of this approximation? The original order of the approximation is h to the n, right? Because it was O of h to the n. That's what we mean by the order of the, oops. I should say it's order n instead of order h to the n. That just means it's order of h to the, it's O of hn is the error term. Again, that O, I don't care a lot about the understanding of the O of hn. If you're in other classes where you talk about algorithm analysis, you'll talk about big O and big theta and big omega functions. Okay. What I want you to understand about the O for our purposes is that the error term here involves powers of h. The smallest power of h in here is n. That's what that thing means. And again, we think of h as a small number. The smallest power is the one that's going to dominate the error. Right? Because the bigger the power you take on a smaller number, less than 1, the smaller the number gets. So the important term in the error is the smallest power of h that you have. That's what I want you to get, the understanding that I want you to get out of the O of hn right now. Okay? So Q of h is an order n approximation. Okay? What did we do? Well, we got rid of the n approximating part, right? We got rid of the h to the n. So this new one, the new function is order n plus 1, at least. And by at least, I really mean at worst. It could be better. Remember, again, we've got all these 2's that we divided through, right? So we've actually even cut the error down by even more because we're dividing through by those 2's. Okay. So what we've done, I mean, it does involve, obviously it involves a little bit more work when doing these function evaluations, but depending on the function, we've cut down on the error that's introduced by the h's. So if we can do these computations a few times, maybe we can get the error cut down quickly without having to do those machine representing problems with cancellations or the subtractions. Remember, the whole point of this is to try to get the approximation as fast as possible. Remember when we did that approximation for the derivative of sine, we had issues with the subtracting numbers that were too much alike and got 0, right? So again, the idea here is to try to get the approximation faster, so we try to avoid some of those other problems we get when we have two numbers that are really, really close together. Okay? All right. So how does this help? Well, once we have an approximation, I can cut down the error by doing this formula, which means that if this is my new Q of H, I can do the exact same trick again. Okay? So, for example, say I have Q of H. I can obviously compute Q of H over 2, right? And from those two, we can get this 2 to the n Q of H over 2 minus Q of H all over 2 to the n minus 1, right? Do you agree with that? Okay. Well, say instead of h and h over 2, I did an h over 4 here. Nothing special about it except that I just halved the h again. These two now, again, these two are also approximations to that original f, right? Remember, this f here is a constant. No matter what I replace the h with, that f stays the same. Right? No matter what I replace the h with, the f stays the same. So this Q of H, this Q of H, this Q of H over 2, this Q of H over 4 are approximations to the same quantity. So is this one, right? But if I use these two now instead of these two, I can come up with another formula that looks like this, except instead of h here, we would have what? H over 2, and instead of h over 2, we would have h over 4, right? So I could do 2 to the n q of h over 4 minus q of h over 2 over 2 to the n minus 1. Right? We agree with that? Now, in these here, this is some function of h, right? I mean, there's an h in it. It's some function, yeah.
When you change like that, you can look more than 2 to the n differently?
No, it's the same. Because it's just going back up here. I shouldn't change up here because if you do q of h over 4 here, you would have that expression, right? Okay. This one here, this is 2 to the 2n. This is 2 to the n. So I still need to multiply by the same 2 to the n to be able to cancel out that. Because I'm thinking about, I'm not worried about the first one now, I'm just worried about these two.
Yeah.
So I multiply by the exact same constant. So it is the same 2 to the n. Yeah. It's a good question. Thanks for asking. I do appreciate that, but it is the same one. This is, by the way, this stuff's all new to me too. So asking me questions about it, make sure I get clarification is great because it makes me think about it more too. It's kind of funny. I was talking about doing this today, and Dr. Ruff goes, "What? I've never heard of that." So it's brand new to everybody. It's kind of fun. All right. Anyway, this is that thing that I just put a brace over the top of. That is also a function of h. So let me just give it a name. Let me call it chi of h, because I'm just going to give it a Greek letter, because that's fun. Greek letters are fun. What's that? No chi? Oh, sorry. I didn't put a squared on it. What's it? You want me to do a different Greek letter? I already wrote that one. Chi's a good letter. Plus, if you do math type or use the equation editor on Word, I believe if you hit Control G and then hit the Q, you'll get a chi. That's what it works with my word processor that I use LaTeX for to do math processing. It's Control G and then hit Q, and it gives me a chi. That's why I use chi. Literally, that's why I used it, because I hit the Q to get a chi. It's logical. At least in my brain, it's logical. You don't want in here, though. No one wants in there. It's way too much crap in there. All right. If this is, call it a, well, you can make it look like a psi if you want, the way I wrote it. Just tilt your head slightly. Looks like a psi. How does this function here relate to this function over here? What's h been replaced with? Yeah, it's h over 2, isn't it? So I can write this bottom one here as chi of h over 2. Again, both of those are approximations to the same f. Now again, the whole point of this is the functions on the left-hand side are of order n. These new functions are of order what? N plus 1, right? So if I interpolate with those, or extrapolate with those two functions, I'll get a new function again, same form, but what will its order be? N plus 2. Yeah, because you're doing the exact same thing. I don't know why I squeaked, because I was very excited about it, apparently. N plus 2! All right, but these are both of order n plus 1, so if we extrapolate again, and I use chi and chi of h over 2, just for making the notation a little bit nicer, I can do the exact same thing with these two, and get 2 to the n chi of h over 2 minus chi of h over 2 to the n minus 1. And now I've made an order n plus 2 approximation. And now you can imagine how I could keep going with this. I could make another row with a q of h over 8, right? Just have it again. I could do the same thing here with q's, and do the same thing here with chi's. Oh, and now I've got 2 that I work with again, right? I've got 2 I can work with again and make another approximation with the order n plus 3. And then I can make a new row and get another approximation that's order n plus 4. And now you can see where this might play into Excel, right? This one uses these 2, this one uses these 2, and so on down the line. And then notice the formula is the same when you go to the next column. Just going down to the right, making a triangle, right? But again, each of these will give you an approximation of the derivative. But eventually we're going to stop in this triangular pattern and use the last one to give us our estimate. Okay? That's the idea. So let's go see if we can do this specifically for the derivative that we came up with first, and see if we can implement it in Excel, and then see if we can do a similar type of thing for a second derivative and implement that in Excel as well. So last time we talked about that, what the book refers to as a central difference formula. Remember, you had your f prime of x was equal to 1 over 2h f of x plus h minus f of x minus h, right? We agree with that? And then what were your terms on the end? What powers of h did they involve? It was h squared and then h to the 4th and h to the 6th and so on, right? It was all of h squared. But notice it was only the even powers, right? And just to, I'll put minuses. It really doesn't matter because I'm not worried about what they are. I'm not worried about the constants. Your book uses minuses. It doesn't matter if they're pluses because, again, they're just constants. And the constants could be negative, so they might be pluses anyway. That was really weird. I would just go to the chalkboard and say, sorry about you, Susan. She got 30 minutes of lecture. Anyway, notice that the powers here for your h's are all even, right? So notice that when you put in your h over 2, instead of getting a 2 to the n that'll pop out, you're going to get a 2 to the 2n that's going to pop out. Right? And you'll get a 2 squared, a 2 to the 4th, a 2 to the 6th, which is like a 4 squared, a 4 cubed, and so on down the line, right? Because we're missing those h's, the odd powers of the h, right? Right? So we're going to get 4s instead of 2s. So for our purposes, this is our q of h, right? From what we just did in general, right? That's our q of h. So down our first column, we'll have these estimates. And your book gives this, they give it a different notation. I don't see the point in the different notation personally. You're going to have those plugging in whatever h, pick a good value for h. You can always change that value for h later. But that's what your q of h over 2, your q of h over 4, h over 8, and so on down the line will be. Notice in our derivative formula, though, when we want to kill off something here, I have to kill off the h squared piece, right? Not an h, but an h squared. When I put h over 2n, I'm going to get up a 4 in here, right? Right? Instead of the 2. So when I do this, your formula is going to look like what over here? Well, instead of that 2 to the n term is really a 2 to the second term, right? This is going to be a 4 that's in that first denominator, right? So this will be, it'll be 4 times q of h over 2, right? Right? And then minus q of h all over 3. Again, why is it 4? Because it's 2 squared, right? That was why it's 4 instead of 2, right? Because it was O of h squared, right? Okay. And then you would have the similar thing here. You would have the 4 q of h over 4 minus q of h over 2 over 3, and so on down the line.
Then that was chi of h.
So this one was chi of h, this is chi of h over 2, the next one would be your chi's on the other side. Yep, that's right. Okay, yeah, more.
Well, how does your 4 and 3 not change? Because now we're plugging in the h over 4. Like into it.
So those constants don't change at all because, go back up here. Again, when we're looking at this one and this one, we're looking at canceling out a 2 to the n on bottom and a 4 to the n here. So I only need to multiply this by 2 to the n to cancel here. Because if I take the 4 to the n on bottom, multiply by a 2 to the n on top, I'll have a 2 to the n still on bottom, which will cancel this 2 to the n on top when we subtract. So it's the same constants as you go across, because you're canceling the same thing. And that's just an effect of the fact that all we're doing from one step to the next is halving. So when I halve it and then take it to the nth power, I have to be able to undo that halving to the nth power to be able to cancel the 2. So it's the same halving that we're doing all the way down. Right. And then we're going to carry that same formula across. So this is going to be, hopefully, fairly easy to implement in Excel. That was fun. Hopefully this will be easy to implement in Excel. Oh, that was why it was mad at me last time. There we go. The connector started to come out of the surface. That was the issue. Oh, come on. I want to make sure the power cord's plugged in because it's when it goes to the projector, it eats so much power. I don't want the battery to die. That is the added benefit of me recording these. If you go back and listen to them, you get to hear my editorial comments during the middle of class again. I'm not necessarily sure you want to do that. I'm just saying you can. All right. So, remember remember at the beginning of the semester we were estimating the derivative for, what, sine of x at 0.5? When x is 0.5? I believe that was what we did. All right, so for that purpose, let's just say I have an x and I have an h. We'll leave those the same the whole time. So, no, you just have to squint. Thanks. I would have forgotten to zoom in until somebody asked me. Thank you. Just think you have a few more classes to take with me, too. All right. So I just want to make this easy. So I'm going to put the 0.5, and let's say we start with an h of 0.1 for argument's sake. I do want my h to be less than 1, because remember, again, the argument is that the lowest power of h is what's dominating our error. Well, for that to work, I need to take higher powers of numbers smaller than 1 to make them smaller. So if I take numbers that are bigger than 1, then bigger powers dominate, not smaller. So we want to make sure that our h's are at least below 1. Otherwise, the whole argument that we're making doesn't make any sense. Right? So in this first column, again, I want applying the formula to, well, I'm going to put something else in the first column. I want to apply the formula to the h's being divided by higher and higher powers of 2. So actually what I think I want to do here, just to make things a little simpler, I'm going to add a column. So I inserted a column in there, just so that I can run down powers of 2. So, and in particular, for our purposes, our powers of 2, well, no, I don't want powers, never mind. I want 0, 1, 2, sorry. It was just, I was saying something that was not going to be right. So I stopped so I didn't get a tick mark. Right. So here I'm just going to keep track of my powers of 2, because remember your first column is just going to be Q of H over 2, Q of H over 4, Q of H over 8, and so on down the line. It's going to be Q of H over 2 to that power. Right? Okay. So, if I use the Q of H that we were talking about before, our Q function, which I think I used phi last time. I was looking at a different book when I was preparing for class today, another textbook. The Q function is that function we just were doing a minute ago with approximating the derivative. It'll be that 1 over 2 times h times f of x plus h minus f of x minus h. Right? So our 1 over 2 times h, well, remember we want h, whatever this h is here, I'm going to replace it with this by, h over 2, right? Right? So I want to take this h here. Oops. Oh, I didn't hit an equal sign. Problem. Equals. I want to take this h. I don't want that h to change, so make it an absolute reference. But I do want to divide it by 2 to the exponent that's over here. I also don't want that reference to change by column. I do want that reference to change by row. Because again, we're going to plug this number in as we go across, right? Actually, I'm starting to do that. Yeah, let's make it an absolute cell reference to start with, and we may have to go back and... except I do want to change the row number as I copy down. So let me change it to hold the column constant, but not the row. So far, so good? All right. So then I want to close off that parenthesis and the next one. So again, the whole reason for this, remember, it's 1 over 2 times h, but I want to replace these h's with h over 2 to a power, right? As we go down the row, or down the rows here. Okay. So that's why I've got this extra divided by sign in here with a 2 to a power. But I want to make sure I change the rows because I want to get 2 to a power each time down this column. Right? And then, again, when we're doing back at the beginning of the semester, we were doing the derivative of sine. So let's do sine of, I want my B2, which is my x. Let me make that an absolute reference. Again, I'm setting this up so I can change that x and that h to see if we can estimate derivatives at other places. So the reason why I'm doing that. Okay. So this would be sine of x. I want to add h. So I want plus. H is here. I want absolute cell reference. But then again, those h's are the things that I want to divide by the powers of 2, right? So here I want to do 2 to the power. Again, I don't want the column to change. Actually, I don't think I'm even going to move that one anyway, but that's all right. I don't want the column to change, but I do want the row to change. So I'm going to put an absolute cell reference on that A. I won't change the column at all. But I do want the row number to change. Again, that's for us to be able to replace. That's for us to be able to replace the h. The C2 is h. That's for us to be able to replace the h with h over 2 to powers, right? Because again, down the first column, we want q of h over 2, q of h over 4, q of h over 8, and so on down the line. Now I want the exact same expression, except I want a minus sign in the middle. Right? It's f of x plus h minus f of x minus h. So it's literally the same expression here. I just need a minus in here instead of a plus. Right? So in that case, I should just be able to highlight that and copy it, and then paste it, and change it to a minus. And then I should have one more parenthesis to put on the end. And I know it looks ugly, but because we had all those cell references in there, along with the absolute references in there, which is why it's ugly. But again, the formula is just 1 over 2h. I need parentheses around the 2h because it needs, that whole thing needs to be in the denominator. This part right here is just our formula for the h as it's changing, right? And then it's times the f of x plus h. So again, this second formula here is just to give us our expression for the h, how it's changing. And then minus f of x minus h. So again, that was our central difference formula for the derivative. Yeah, Julia.
Why is it sine?
Why is what sign?
Why are we doing sine?
I'm just redoing that example that we did back at the beginning of the semester when we did derivative of sine. My function here is sine of x. Yeah, so I'm estimating the derivative of sine of x at 0.5.
Oh, okay.
Yeah. That's why I chose sine, because that was the one we did at the beginning of the semester. Yeah, great.
Why? Where does the 2 to the base 3 come from in the very beginning?
Here. So remember, as we go down here, we want those. Nope, that didn't work. This way? Yeah, that was it. As we go down the first column, I want to use my q of h function, but I want to replace it with h over 2, h over 4, h over 8. So that's where this is coming from. So that the first one, when I put 0 here, I just get 2h. When I do the next one, I get h over 2. I do the next one, I get h over 4, and so on. So that's just a quick way to get me those powers of 2 in the denominator. Is it okay for me to hit enter yet? You good? Okay. Hey, I didn't have an error. All right. So now I should be able to just take this and copy it down. Now again, each of these is an approximation to the derivative of sine at a half. Okay? But remember again, as we are going to move this over to the right and down, my approximation, the errors in my approximation should get smaller. Okay? So now remember, for this cell here, we're going to take 4 times that one, subtract that one, and then divide by 3, right? Yeah.
So now if you could put the formula that formula I got.
You know, that was it's a little bit bigger.
No, you need the one on the front. You need the one. B plus C2 divided by 2. Parentheses closed. Close the one at the end. One at the end. One divided by 2 times C2.
So yeah, do you want me to send this one and paste it? Well,
Let's try it.
Sine B2 plus C2 over 2. Can you do me a favor? It's either enter or escape. Go to right click on that cell. Yeah, on the cell. Go to format cells. Maybe. Yeah, it's formatted into 0 decimal places. Go to general.
Do I just change?
No, that was when it was 0 before
Go
it fixed
to
it.
general. Go to general. And just hit OK. You're just fine. Or well, it's still off by something. It's not the same number. I don't have it entered in.
whoa!
Copy it down and see what happens.
Wait, that's the same number.
8, 7, 6.
Yeah, you got it now. That was what your problem was there.
Amy has a problem.
Yeah, I know that.
That's independent of this one. That's independent of this class.
What's going on? What are yours?
I can't figure it out.
You get too many parentheses on the end.
But I don't
You need to write parentheses after
That's what I'm doing
C2.
today.
Or, no, you don't. That's no, you don't. Never
I
mind.
do this.
Sorry, I lied. Okay, yes. Then just delete.
There you go. Anybody else having issues? Good? Good, good, good. Phew. All right. So again, the next one over here is going to be what? Do you remember? It's been a while since I was talking about it. It's 4 times which one? Yeah, the one beside it, right? And then minus the one above it. and then divide by 3. Now look, all of these look exactly the same, don't they? Well, these were changing a little bit. These were all the same. So this is probably, well, especially the first 5 digits here. But again, if we should be able to copy this over one spot now, and then copy down, and now nothing is changing. So notice how quickly, even though we did a few more computations, notice how quickly the approximation for the derivative settled down. And notice all I did was just copy over and paste down as I moved from column to column. Because again, remember, I can think of these now, I can think of these as my new Q of H and Q of H over 2. And then it's the exact same extrapolation formula. And from here on, if you just kept copying and pasting down, you should get the exact same derivatives. One of the reasons why I had you do it in terms of the x and the h here is because now you should be able to change and see what happens if you just started playing around with different starting values. For example, maybe I did 0.2 instead of 0.1. Well, notice that hardly anything changed at all, did it? Right? Still end up in that same spot. What if you changed your x value? Well, for example, we should know that the derivative of sine at 0 is 1, right? So if I put in 0 here, we should be getting 1 out, which we do. Right? Or if you wanted to do, say, pi over 3, because it's pi over 3, because again, the derivative of sine is cosine. Cosine of pi over 3 is a half, so I should be getting something that approaches a half here, right? Which we do. And notice again how quickly this is doing this, right? In a few steps, which you can implement on a computer or Excel, clearly. In a few steps, you're getting a really, really good approximation. I mean, you're getting exact values at this point. But you're getting really, really good approximations to the derivative. And again, if it wasn't, notice I stopped because it settled down, and clearly I was getting 0.5 everywhere, right? But if it didn't settle down, you just copy over again one spot and paste it down. Copy over a spot and paste down. You get better and better approximations.
So if when you're moving down the column, the reason the derivative is getting more accurate is purely because the x is getting smaller, right?
The h's are, well, if the error is getting smaller, because we moved to a different spot where the order is going up for the error. Because in this first column, the order of the error is 2.
Yeah.
In the second column, it's 4.
Oh no,
Now,
man, when we move down.
Oh, yeah. The reason why it's getting better is we move down because the h is getting smaller, right?
Yeah. But on this one, it's because of the trick we used.
Yeah, exactly. And we're going across this way. Because if you were doing this on a computer rather than Excel, you wouldn't copy all of these things down. You would compute these two, go here. Oh, I need to do another one, so then I'll compute this one and go here, and along those lines. You would do it as you needed it rather than pasting down in an Excel spreadsheet. Because on a computer, you're more interested in saving the number of computations you actually have to do if you're actually doing a program, depending on how many iterations you have to do to get the approximation accuracy that you need. Versus, I'm just trying to show you the technique on Excel, so we're just pasting it real quick so we can get what we need quickly.
So this trick, right? This can be used as long as we have an approximate function on anything. Right?
Correct, yeah. The exact same trick will work. Which is why we can also use it to do integration, for example. We'll see how to do it. We'll see how to implement it with a trapezoidal rule, for example. And I can do this and it doesn't have to be just first derivative. We can come up with a formula for the second derivative and do the exact same thing. And approximate second derivatives or third derivatives or what have you. The same trick will work every time. It's a clever trick. I had not seen it before. It's neat how it works. At least I think it's neat how it works.
So why did you guess the H value that you did?
Oh, I just used one. Yeah, you can. Part of that is the function that I'm using right now is a simple function that the computer knows and can approximate really, really well. But in other things, if you use an H too small, you might get outside of your machine accuracy too fast, and it'll give you errors or just give you 0. So you may have to make it bigger so that you can actually see convergence, so that you don't get below the limits of the machine accuracy to start with. But usually it's arbitrarily chosen. You just may have to play with it to see what works best. I just use 0.1 just because.
Okay.
Yeah. Do you have a question?
Yeah, in a little
In a little bit. Okay. I'm on pins and needles now. Okay, Morgan.
So as you go down, your H's are getting smaller.
Correct.
But then as you go across,
The error is getting smaller.
okay. Is that because like we're building off the previous one?
Yeah, we're building off the previous one to kill off those lower powered terms and getting higher powered terms for A. Yeah, so we're building off of those to make the error. So we know that we're getting more accurate. And really, again, what we're interested in, again, if you were doing this on a computer and programming it, you would be computing these ones down the diagonal and only getting the ones across as you needed them if you needed to compute another one. You would be checking from here to here, is my accuracy okay? Well, no, so I need one more, so then you would compute. So you would check this one, and clearly those are far apart, right? So then you would compute this one to get this one, and then compare those, and then see again, okay, my accuracy is probably okay, but if not, then I'll go here and compute these across, and then I'll compare those two and see if my accuracy is okay. If you were doing it as a program, you would compute them that way. Since we're doing it in Excel, we just went and just copied them all down. Yes? You were laughing?
Okay.
Oh, laughing at Haley? That's fine.
You said,
Oh. No. Well, yeah. I figured that was what the laughter was for. Okay, so let's see if we can do a similar thing for second derivative. Just because.
So
You did sound upset about it.
So when we're doing these approximations, we have to have the case that x is smaller than 1. I mean, in derivative it works because we're trying to make that edge as small as possible. But when we want, is that when it's the case that x is greater than 1, we can't use this method?
You probably can. It's just that you're going to be those first terms that we have. It'll depend on, well, because eventually, as you do your powers of 2, your h will be less than 1.
Yeah.
Right?
Yeah.
Whatever h you pick. It may just be the case that if you pick a bad h at the top, your numbers are going to be goofy at the top, and may make more errors as you go down, or just they make the convergence a lot slower. It's a matter of trying to get the convergence as fast as possible. If you're using big values of h, then your convergence is going to slow for certain. And if we think about remember again, the way we got this first formula for derivative was using power series. It's also possible if you use too big of an h, you're outside of the interval of convergence for the power series. So then you got really, really bad approximations for what you're trying to do. Because as far as power series go, if you have an interval of convergence or a radius of convergence for your original function, that radius of convergence stays the same no matter how many times you differentiate. It never goes up or down. You might gain or lose an endpoint convergence, but the radius always stays the same. So if you have a power series and your radius of convergence only works for h values that are less than, a half, say, but I don't want to use an h that's 1 because I don't even have convergence on my power series and have a really, really bad approximation to start with, which is my guess would throw everything off. So my guess is with these simple functions that we're doing, especially with sine, since the power series for sine converges everywhere,
Yeah.
I'm guessing it won't matter what you use for h. Eventually you'll get to the derivative that you want.
Yeah, but yeah, it's certainly nice.
Yeah.
I didn't realize that we're constantly dividing by the powers of 2.
Yeah, the constant divided by the power of the 2 will get your h less than 1 anyway.
Yeah.
But we definitely want to make sure that when we're talking about the error analysis that our h has to be less than 1 if we're going to be talking about the smallest power bounding it. Yes.
I have a question about that.
Okay.
What is dividing differences?
We did the divided differences.
Something we did like
We-
last Tuesday.
It was that table we made. We made a table with that too.
The f of x1, x2, x3 thing, right?
Mm-hmm. Yep. You have the x1, x2, x3 thing with the square brackets. That was the notation.
Is that instance method?
It was after. It was after the Newton's interpolation polynomial.
Okay. So that is called divided differences.
Yeah, it's called divided differences. Yep. Yes, Chelsea. Chelsea, do you have a question?
So that is what, my Excel is around a lot farther. Yes,
Let me see.
it's a lot bigger. So,
Oh, that's okay. I mean, I think it's just because mine said that if I expand my columns, it'll probably have the same decimals yours does.
that's what I was wondering.
So if I do,
I guess that makes sense. Okay, that was easy.
yeah,
I didn't like that out of those numbers.
yeah,
It bothers me.
yeah. So notice here, it depends on your tolerance level too. So notice here, there is a difference between these two. If that wasn't in your tolerance level, you'd still need to go do another iteration. Yeah. Yep. That was probably what the problem was, though.
Yeah.
Okay.
That was better.
Okay. All right. Let's talk about if we can do a similar type of thing for the second derivative and see what happens. See if we get an approximation for the second derivative. All right. So remember again, we had our power series for x plus h. That looked like our f of x plus f prime of x times h. 1/2 f double prime of x h squared. 1/6 f triple prime of x h cubed. 1/24 fourth derivative h to the fourth, and so on. We had that last time. We talked about where that came from last time, about centering it at x and plugging in x plus h for x, if you will, I suppose. That was a bad letter to use. But anyway, the reason this h is coming in here is because we're doing the difference between x plus h and x. That's where the h's are coming from. All right. If we replace the f of x plus h with the f of x minus h, we still have f of x here. How does the second term change? It's negative, right? The third term stays positive. That second derivative term stays positive, right? Because we're squaring the h. Right? The next one is negative. The next one is positive. And so on. Again, we're trying to get a formula we're trying to do the same trick that we did last time, trying to get a formula for the second derivative rather than just the first derivative. And remember again, a lot of the point of doing this, of course, is to try to do it involving only the function. You're trying to approximate the derivative without actually having to take the derivative. Right? Or again, here, trying to approximate the second derivative without actually having to take a derivative. Okay? So, if I want to try to get to solve for the second derivative, I don't want those second terms to cancel, right? So if I want to try to solve for the second derivative, what do you think I should do with these two so I see the second derivative? Just add them, right? Notice when you add them, what happens to the odd powers of h? They all cancel, right? So when we add these together, you'll get f of x plus h plus f of x minus h, and then minus f of x, or equals, 2f of x. Right, when we add these two together, we'll get 2f of x. The first power of h will cancel. We get a plus f double prime of h squared, that's double prime of x times h squared. The third derivatives cancel. It'll be a 1/12 if we add those two together. I don't really care what the constant is. H to the fourth, so on down the line. Can we solve that for the second derivative? Yeah, right? So if we solve that for the second derivative, we would need to subtract the 2f of x over to the other side and divide by the h squared. So we would have f of x plus h minus f of x minus h all over, oops, sorry, I forgot my plus, I subtracted the wrong thing. Minus 2f of x plus f of x minus h, got ahead of myself, over h squared. Right? And then we got a minus a bunch of those things. I'm going to leave them on the same side as the f of x, f double prime of x, because this term has h to the fourth, the next term will have h to the sixth, the next term will have h to the eighth, and so on down the line. What order does that have? What's the order of the error? H to the fourth, right? That's the smallest power of h we have. So on this left-hand side, I can think of this as being plus O of h to the fourth. Notice here we've got a formula for the second derivative. Gives us approximations for the second derivative involving only the function values. And it's a fourth order approximation, meaning again the error is in terms of the fourth power of h. But we could do interpolants like we did, or extrapolants like we did in the previous thing. Just like we could do the same idea with the extrapolation to get better approximations by using higher powers of 2 in the denominator again and rearranging things. Now notice again, the only things that are left are even powers of h. So those coefficients again will be 4 and 3 in the numerator. Right? If you had single power, if you had h's going up by 1, each time you would have a 2 and a 1 in the denominator, so you wouldn't have to divide by anything. The reason why we had a 4 and a 3 was because, again, we had those even powers of h's left. So really there was a 2 squared that was left over. That was why we had the 4 and the 3. But in general, if it was just going up by a single power of h each time, we would have a 2 and a 1. Okay. All right. But again, you can implement this formula in Excel just like we did with the last one and get approximations for the second derivative. That's okay? All right. So next time we will talk about what to expect for your quiz.
That's open note, open everything, right?
No.
Open heart.
Open heart? Yes.
Open mind. That's good.
It'll be laparoscopic. It'll be fine. All right. Have a good one. We'll see you later.
And do the homework.
I am. We got to do dance cop first, so.